Thank you very much for the invitation to give this seminar at the school. It's a pleasure for me to be here. As said, I'm a member of LSB experiment. So today I will talk about recent results in exotic spectroscopy, mainly from LSB. So starting from general introduction, as you might know, exotic hadrons have been predicted originally by Gell-Mann and Zweig in the first formulation of the quark model. But the first searches for those hadrons in the light quark sector were without success. Indeed, we had lots of experimental evidences in the heavy quark sector, especially in the hidden charm sector. I just put here all the states. Oops. Okay. Let me do it again, sorry. Okay. Yes, I just put the wrong, okay. So I just put here the hidden charm-like states taken from this review I will talk about later on, where you see all the conventional hadrons in green. And the hidden charm sector is the ideal place to look for exotics, both from a theoretical point of view and experimental one, since the theoretical models are well established for conventional states, and from the experimental side, it's easier to measure them, since they are narrow and non-overlapping. The charmonium are narrow and non-overlapping, and there is a good agreement below the DD bar threshold. Therefore, lots of exotics have been discovered in the past few years. So here are reported QQ bar-like states, or tetra quark with charge states, or even with strange quark content with the widths, measured widths. So as you know, the nature of this state is still unresolved. Indeed, we are still investigating how quarks and gluons bind together inside those objects, while we just observed the hadrons, the color singlet mesons and baryons in nature. And a lot of phenomenological models have been put forward to describe how quarks bind together. And as you know, they fit into these categories: compact tetraquark or pentaquarks, hadronic molecules, but they could also be due to hybrids, global, or a mixture of all these models. And it's worth to mention that the states could also be mimicked by rescattering effects. Nowadays, I've seen you made lectures about this, so you know it very well. Nowadays, lattice QCD is becoming a powerful tool to describe predict conventional and exotic states, and we think that we expect it to play a leading role in the near future, and so to help clarify the nature of these states. At the moment, there is no consensus yet on the nature, how we can describe, let's say, the binding of the quarks and gluons inside this object. And the question how to discriminate among those models is not easy to answer experimentally. So I will focus from the experimental side on what we can do in experiments to help guide the theorists to formulate models that are realistic of what we really measure in experiments. So what we do is essentially to study different decays and production mechanism of exotic hadrons that we have observed, to measure precisely their parameters, mass widths, and quantum numbers, as well as to try to find multiplets of isospin as in the conventional sector. So, as you know, of course, in recent years, from the 2000, more than 50 new hadrons have been observed. containing an heavy quark, so a C or B quark. And it deserves, since it's like a renaissance of the spectroscopy, so it deserves to be called a new particle zoo, like in analogy to the particle zoo of the early 60s for the conventional hadrons. And so to help clarify and unravel into this new particle zoo, we made recently a review called The Brief Guide to Exotic Hadrons, which has just been accepted by Modern Physics Letter, where we try to, let's say, make an introduction and a collection of all known exotic states that are also listed in this table from an experimental point of view, and is mainly intended to newcomers to the field. And it's like a guide to a new landscape, and it follows the example of a field guide. So we try to collect all known states into cards, collecting states with similar properties like a number of quarks, flavor content, isospin, as well as spin parity, production, and decay channels. And this is just the example of one card for the KC-13872. Where you see all the characteristics of the features of the states, like the experiments where it is observed in, production mechanism, as well as the decay modes that are allowed. So I hope it can help to figure out all exotics and to remember them. And this is just a funny picture where you see that all states are peaks in these of these mountains. Of course, for brevity, today I will mainly focus on the Hadron Valley, so the LAC results, and in particular on the LACB one, since I'm a member of this collaboration. Yes. Yeah, it's exotic composed of 6 quarks. So LACB has been the major player in spectroscopy recently. It discovered more than 20 exotic hadrons. And this was possible thanks to the very high invariant mass resolution that we are able to achieve. So thanks to the precision on the momentum. The separation, we have reached detectors, Cherenkov detectors to distinguish between charged hadrons. And this is essential for all spectroscopy studies. And it has a highly performant trigger. So far, during run 1 and run 2, it collected a luminosity of 9 inverse femtobarn. But I want to anticipate that now we are in run 3, and last year we already collected the same amount of data of the previous two runs. So new results will come out soon. Which kind of analysis techniques do we use in spectroscopy? First, worth to mention, we could just, in principle, perform an invariant mass fit to the invariant mass distribution. This is an example of a pentaquark analysis. That in order to come out soon, we decided not to enter into the detail and just perform a simple fit using Breit-Wigner functions to extract, and this allows to extract properties of the states like the mass and width, but of course not quantum numbers. So in order to extract the important properties of the quantum numbers, we need to perform a full amplitude analysis, which is in brief, it's based on the description of the phase space of a decay of interest. using a model which usually is based on the helicity or the tensor formalism. And the resonances are described by a line shape, Bride-Wigner or K-matrix, or whatever, but which is usually model dependent. And then we perform a maximum likelihood fit of this model to the data to extract the parameter of interest and to account for, and this is, let's say, crucial to account for reflections from other resonances that may occur in the decay chain. Just to say, we usually perform, since this method is model dependent, we usually perform also moment analysis, which are just expansion of the amplitude on the basis of the Legendre polynomial, which can be, let's say, a model independent check that the resonance is that, let's say, the data are not model only with non-resonant contribution. Okay, so starting with the first exotic candidates observed, you know well that there are two candidates observed in the same year, in 2003, the KC-13872, which is the most known exotic state, and the ELISABETTA star seen by Babar in the isospin violating decay of to ELISABETTA pi 0. Regarding the KC-1, the nature of this state, of course, they are the first one, but the nature of this state is still not known. It's controversial, since they could even be conventional, just conventional charmonium or conventional open charm state. Regarding the X, it is the most known, the most studied exotic state ever. After its observation, 10 years after its observation, the SPN is measured by LSEB to be 1++, which make it consistent with the KC-1 2P state, so just a conventional state. However, it has lots of properties which do not fit well in the charmonium spectrum. The mass is consistent and is exactly at the threshold of a D0 D star, and disagree with the quark model calculation by around 100 MeV. And the width is surprisingly narrow, around 1 to be above the open charm threshold, and these are around 1 MeV. These plots are taken from this paper by LSEB. Its nature, so although it's very well studied, its nature is still under debate. We are still investigating whether it's a conventional or it's molecular state or a mixture of more than one model. And today I want to bring you to a couple of recent results by LSEB on decay processes of the X that could help clarify the nature of this state. First of all, one of the, let's say, the mysteries of the X is the large isospin violation observed in the KC-1 decays. And here we want to measure how large this isospin is in the KC-1 to J psi pi decays. Previously, as seen by this plot from a Fermat Atlas analysis, the only contribution that dominates the phase space in B to J psi pi k decays was the isospin violating component, so the decay through the rho. While recently, with an analysis of LSEB, was possible to disentangle the contribution of the omega, which is about 2%, but can be enhanced to around 19% by the interference with the rho. And so through the ratio of the isospin violating and isospin conserving coupling, we can measure how big is the isospin violation in this decay. And it's of the order of 0.3, which is much larger than what is expected for a charmonium state, something like 0.05. So this could be an indication that the KC1 is not a pure charmonium-like state, but is also likely interpreted as related to the mass splitting between the neutral and the charged thresholds, which are very close in mass, and in particular the X, remind you, is at the threshold, at the neutral threshold. So this is one of the analyses. The second one regards the radiative decays of the X. Even in this case, it was thought that the radiative decays can help understand the nature and distinguish among models. And here I present an analysis of a KC1 decay into J-psi photon or psi2S photon in B decays at LACB. We performed a four-dimensional fit to these variables, which are the first two related to the decay through the psi2S and the second two through the J-psi. And it is worth saying that even though there was some evidences before of a decay through the psi2S, this is the first observation of these decays, where we reach overall more than 5 sigma. And we measured the ratio between these two decay rates, which is comparable with previous results, especially from Bavar, Bell, and the previous measurement from LACB. But there is a bit of tension with the upper limit from BEST3. So what can we say? Since this ratio is very large, can we say something about the interpretation? Yes, a bit, let's say. There is, since the ratio is very large, this is an indication that there is a sizable charmonium or compact tetraquark component, which are more likely. However, while the pure molecular DD star hypothesis is questionable, however, there are some predictions where just a small admixture of CC bar component is sufficient to explain the data. So in general, it seems most favorable to have a charmonium or compact tetraquark component, but the molecular is not completely excluded. So it could be a mixture. Okay, since on the contrary, let's say to the X, many other states have manifestly exotic quantum numbers, or because of state with 5 quark content, or because of charged or composed, not of hidden charm, but with the open charm or doubly charm states as a TCC 3875. So I will go through all of these results in the next slide. And today, to guide you through, let's say, through all the discoveries made by LACB, I will just use this slide and classify exotics in these categories. So hidden charm pentaquark, hidden charm tetraquarks, and what is beyond hidden charm. So starting from the hidden charm pentaquarks, we observed 2 types of pentaquarks. So PCC bar, which are hidden charm, and hidden charm with strangeness. So the first observation of pentaquark states is done by LACB in lambda B to J-psi PK with run1 data. We perform a full amplitude analysis, and we observed basically 2 structures of very large width. However, few years after adding the run2 data set, it was possible to see a new peak, first of all, very narrow, at mass 4312, and to resolve the 2 peaks, to resolve in 2 peaks, the one at mass 4550. So thanks to the higher statistics. This is, as I said before, it's a 1D fit that was done just because since we had lots of data performing an amplitude analysis, is really challenging. We are still doing it right now. And so the results will come out, but we prefer to publish these before. And as you see, the pentaquarks are just few MeV below this threshold of open char sigma CD meson thresholds. Afterwards, there was also an important search in B meson decay of pentaquarks. In particular, this decay can offer, it's a good candidate, let's say, for searching for pentaquarks, either in J-psi lambda or in J-psi antiproton. We were able to make a very clean selection of the mode of interest. So this is the variant mass of J-psi lambda proton, where you see the very high purity. And looking at the Dalits, there is a band, like a narrow structure in J-psi lambda, very close to the edge of this distribution. So we performed an amplitude analysis and we fit this structure with a relativistic Breit-Wiener function and observed, let's say, a peak consistent with a mass of 4338 MeV and a very narrow width. Thanks to the amplitude analysis, we were able to measure the spin to be 1/2 and the negative parity preferred over the positive one. This is a very narrow state, close to the threshold of psi CD minus and in S wave. So it is interpreted as either a molecular state or a triangle singularities. I want just to bring you the attention to these two other results of evidences of pentaquarks, but these are just with free sigma significance. So the first one is a pentaquark with strangeness in J-psi lambda, psi B to J-psi lambda kaon. And the second one is the evidence of a pentaquark in Elisabetta to J-psi PP bar decays. Both of these results need a confirmation in the near future. So we are going to update them soon with RAM-free data. So since many of the pentaquark states observed are very close to the mass threshold of the charm barium and meson combinations, we wonder if this is just a coincidental or an evidence of a bound state. And in addition, it would be interesting to search for that in prompt production, so in a different production mechanism, as I said in the introduction. So we tried to do it in LSCB, so just to look for, perform an inclusive search for pentaquarks decays into sigma CD or lambda CD combinations. So these are directly producing PP collisions. And these are all the combinations that we tested. The crossed ones are statistically limited, but we didn't find evidence for neither the old state nor new states at the moment. At least we didn't find observations. And we put upper limits on the rays, making a scan of the width in a reasonable range between 5 and 15 MeV. This is just an example of the mode with highest global significance, which is around 3.6 sigma. And it's the lambda C pi plus D minus mode, where we see an enhancement around 200 MeV above the threshold of this decay. And this, again, it will be an interesting study to perform with the upcoming RAM-free data. Now, let's move to the hidden charm tetraquark sector with neutral states, neutral tetraquarks observed in J-psi phi. This is one of the first, let's say, it's interesting. I want to talk about it because it's one of the first measurements we made, where we as LACB, where we observed tetraquark states. In particular, the first state of this kind, the KC14140, is seen by CDF, and then later on by many other experiments, but with different let's say slightly different waves. LACB was the first experiment that made clarity on the structure of this state. First with a run-1 analysis where 4 peaks were observed with spin 0++ and 1++. And later on, at the run-3, was possible to observe that the run-1 model, as you can see, is not fitting the data in JPSI-Phi. Therefore, 2 additional states were considered. And there is also some hint of structure in JPSI-K+. I will talk about this in a few slides. All these states could be candidates for conventional charmonium states. For instance, the KC1 4140 is a candidate of the 3p excitation, but could also be a molecule is interpreted as a Elisabetta star molecule or as a cusp. On the contrary to the previous results, which were neutral, the first tetra quark with charge is observed in B meson decay, in particular by Bell in 2007, seen as a structure in Psi2S pi. So it's decaying to Psi2S pi. And this is just to point you out that this is the first, let's say, the first tetra quark with the hidden charm tetra quark with charge quark content. You can find more, not read all these details. You can find more in the review if you like. Now, it's becoming very popular, let's say, to search for partners of the tetra quarks. And in this case, I want to bring you the attention to a tetra quark with strange quark content. So these, as said before, these states are observed in the same decay channel that I mentioned previously. So especially to describe data, we needed to structure at mass around 4 GeV. In the same year, also BESS3 observed a state with strangeness just below 4 GeV of mass, and we tested whether it's possible that the 2 states are the same structure. However, for the statistics that we have now, we excluded this hypothesis, and if this fact that the 2 states are different is confirmed in the future, this could be explained as the 2 states with a compact tetra quark interpretation. I point here to one paper from Maiani where he fitted the 2 states into 2 different nonets, 1++ and 1± nonets. So the searches for the isospin partners continues, and we now wanted to search for the neutral state to fill the complete SU3 nonet as in the conventional sector, and therefore we extend the previous decay with the decay of the B0, the neutral decay to JPSI-Phi K short. And we collect, since these two states, these 2 decays are related by isospin symmetry. We collected around 2,000 events. And making a combined fit to the B+ and B0 decay channel, fixing all components of the model to be the same except for the new state, the neutral state at mass 4 GeV that we are searching for, we saw an evidence for it. And this state is consistent to be an isospin partner of the previously observed state, since the difference in mass is just 12 MeV between these two. So one very interesting and important results from LACB regards the fully charm tetra quark. So the tetra quark composed by CC bar, CC bar. And this is seen from production, so directly in PPE collisions. We observed making a one-dimensional fit to the DiGEPSI invariant mass distribution. We saw a structure, a narrow structure at 6.9 GeV. But there is also some deviation, lower mass, close to the DiGEPSI threshold, which deviates from the non-resonant contribution by more than 5 sigma. These results are confirmed by CMS and Atlas later on, where in particular CMS see another state, a lower mass, 6.6, with high significance and an evidence for a fourth state at around 7.2 GeV. However, all these models needs to be taken, let's say the exact values of the waves and masses needs to be taken with caution, because they are dependent to the interference between the peaks. So if we change the description of interference between the peaks and the non-resonant term, the values can shift a bit. So this is, let's say, an example of what means something that is model dependent. Now let's move to the beyond hidden charm sector, so to states with open charm. So we investigated the possibility of this kind of states with open charm, open strange, and here I present some results in BDKs, of course, to open charm. So the first analysis made by LACB was of the B plus to D plus D minus K plus decays, where we, to describe the phase space, we needed, as you can see, both from the Dalits and from the invariant mass distribution of the decay, we needed to add two resonances at more or less the same mass with spin 0 and 1. Decay, so these two states decay to D minus K plus, and are the four tetra quarks with open charm, open strange. Since many models predict its free flavor partner, we search for it, decaying to D sub S pi, and this motivates the searches, in particular in B to D sub S pi decays. So this is what I discussed here, where we analyze a neutral and a charged decay. You see the Dalits, and collected about 4,000 events. And there is an hint of an horizontal band around 8.5 GeV squared, which could be a tetraquark candidate. And indeed, we find it with high significance, making a combined amplitude analysis of the two channels, the neutral and the plus one. And here you see the invariant mass of D0 pi and D sub S pi. In particular, the two tetraquark states with different charge, the neutral and the doubly charged state, are seen decaying to D sub S pi plus or pi minus. And are these components in purple. And the quantum numbers are measured to be 0 plus. The nature, the resonant nature of this state is confirmed by the Argand diagram. You see that the Breit-Wigner, that there is a motion in the imaginary part, in the complex plane, counterclockwise, which is an hint of the real resonant nature. Otherwise, it would not be in this direction. And so this confirms their nature, the resonant nature. Okay, so in summary, these two states are the four-state quark composed of charm and anti-strange quark content plus UD with yes, U bar D or UD bar. The doubly charge is the fourth doubly charged tetra quark ever observed. So the first question we ask is whether they belong to an isospin triplet, and the question is yes, they could, but we need to search for the +1 state. Where is it? So we are planning to, we didn't observe it yet, and we are planning to search for it in the D plus pi 0. In addition, these states have the same mass as the TCS 0 in B2D decay case, so the first channel I talked about, and they could be SU3 flavor partners. Other searches of similar states with open charm, open strange are also going in LSCB, and this is a very recent result, a new result on this channel where we have D0K short in the final state. And again, with an amplitude analysis, we were able to describe the phase space, only including a resonance in the D0K short. This contribution in red, which is observed with a significance of more than 5 sigma. It is consistent with the same state seen in B2D decays, but however, in this decays, it seems that the spin 1 state is missing. So we tried to add the spin. If you remember previously, it was there were two states. I'm referring to. No, there were two states here, one with spin 0 and one with spin 1. And it seems that the one with spin 1 is missing here. So it's evidence it's only at 2 sigma. So probably we are statistically limited, but it could also be that there is something related to the isospin. So the ratio of the fit fractions of the TC1 and TC0 in the two channels, in the two different decays, provide a test of isospin symmetry. And yes, this could be interesting for the future to investigate more. Okay, now let's move to the final result I want to talk about today, which is one of the most exciting results from LSCB, the tetra quark with doubly charm content. Indeed, this state is like the holy grail of exotic spectroscopy. It has been searched for years. First predictions date back the 75. And we observed it in prompt production again, decaying to D0 pi plus. This state is likely an exotic. It has very peculiar features. The mass is few keV below the D0 D-star plus threshold. Indeed, this is the mass difference with respect to the threshold. And it's extremely narrow, 14.8 keV, which is about 10 to 1,000 times narrower, more narrow than any other exotic states. And all the model we used to extract these values relies on these assumptions that the stage is an isoscalar with 1 plus quantum numbers in accordance with the expectation for a CC U bar D ground state. And the fact that as the isospin 0, so it's isoscalar, is supported by not finding any evidence of peaks in the charge, doubly charged channel, so they came to D plus and D plus D0 pi plus channels. We did not observe any peak there. And it relies also on the assumption that there is a perfect agreement with models which consider only the case to DD star. Therefore, about the interpretation, what we can say is that it's likely predominantly a DD star molecule, but a small compact component could also be allowed. So like I refer here to a prediction, so where it is said that. So this state is the first representative of doubly charged, doubly heavy quark hadrons. Its peculiarity is that it cannot decay through quark-antiquark annihilation, because it's, yes, it mainly decays to the D star, with a strong interaction, and therefore it's almost stable against strong interaction. And its evidence supports the existence of similar states, but in the beauty sector, so with two beauty quarks, or a charm plus a beauty quark. And it would be interesting to sort for them in the near future. No, no, it didn't. Yes, only one. Yeah. So I've talked about all these discoveries. This is just a picture where we summarize. We usually use to summarize all hadrons that we observed. Whether we observed about 23 new exotic hadrons, whether there is no theoretical, a coherent theoretical picture, as I try to highlight, with only some of, let's say, some citations to relevant papers. Of course, they're not exhaustive. And these call for more experimental results. And so to conclude, I want to highlight that we are now taking data in RAM-free. We have a new detector, the LCB upgrade 1, which will take data in RAM-free and RAM-4. It's a brand new detector with a fully software-based trigger. It allows operation at higher luminosity, thanks to the fact that we can read out simultaneously with the 40 megahertz collision rate. So we expect we have a 5 times luminosity increase. And we expect to improve the efficiency in the hadronic modes a lot. Therefore, we are really boosting data to a new level. We have already collected 9 inverse femtobarn of luminosity in 2024. You see the proportion, which is the same statistics we collected in the past 2 runs, as I said before. And in addition, we expect around a factor of 2 in statistics per luminosity with respect to RAM-free, thanks to the improved trigger strategy. Therefore, so stay tuned for the first results to come. What we want to do with these results, I highlighted during the talk some, let's say, of the channels that we intend to update, but we want to continue to make more investigations of the observed states, confirming quantum numbers or study the line shape, which could help in understanding the nature. And as well as to explore and find new states, for instance, to access the VC tetraquark sectors as well as pentaquarks with beauty, and search for exotic flavor multiplets, like in this article where they predict many pentaquarks fitting into a multiplet. So that's all. And thank you for your attention. No, yeah, there could be. I mean, we are now we've run two. We are finalizing the measurements, and for some channels we observe just evidence of a decays. So of a decays of interest, so without searching for exotics, but we plan to do it with RAM-free, and I think there could be some hope that we found some in one of his channels. Yeah, there are many. There is one called Sexa Quarks, which is the most famous one. Yeah, yes, with this specific work content, and there are, let's say, there is a big program on this in LACB, so on different channels. Yes. There are some hadrons that can be explained in this way. I mentioned them, some of them during the talk. Let's say, for instance, even the pentaquark with strangeness, the one very close to the edge point seen in B2 Psi lambda antiproton decays, is explained in a paper by Swanson as a triangle singularity effect. And but experimentally, for some channels we tested this hypothesis and we excluded. For some others not. But experimentally, it's not easy to, let's say, to reply to this question. So to find a way, let's say, to say that one interpretation is more favored than the others. So there, yes, if you ask this question because you want to see if there is one state that we establish is not resonant, but is no, we didn't. Yes, we tried, but we didn't find any evidence till now. Yes, the production is too low. Do you ask this question because we did not measure the residues? Let's say we did not. We tried for some analysis to make like a line-shaped study with effective range, in the effective range approximation to extract the effective range. But even in this, for the KC1, for instance, but I know that in theory there are lots of debates between theorists whether this is really a measurement of the radius, of effective radius. So it's not trivial. Also in this case, we are trying new measurements called femtoscopy. And maybe we will have more results. So I think these are more related to the radius of the can extract radius of the objects. But these are just preliminary searches, so there are no results public yet.
models so far on the market for phenomenology, but I mean, today, to date, what is the most likely theoretical interpretation of the occurrence of these exotic states?
No, I didn't want to say that there are no models. There are a lot. Yeah, there are a lot of models. I mean, even they can be categorized into different sectors, but they differ one from the other. So since these states, one of the most popular one are the molecular interpretation, because all these states are very close to the threshold of meson or meson-baryon states. And this could favor the molecular interpretation. Or whether it's not neglected the hypothesis that they could have a core of compact state in the die-quark, anti-die-quark interpretation. So I think there is not a striking evidence that one model, one interpretation is more favored than the other at the current situation. So it seems that it depends also on the states. There are some states that are interpreted more likely, like the TCC, the open charm tetraquark, is more likely to be a molecule. But it's not always true for all this. It's not true for all the states. So there is not a definite answer to this question.
The data at the same time.
Thanks.